Welcome to Manifold. Today, I am super excited to have Scott Aaronson as my guest. Many of you will already know who he is, but let me introduce him as the David J. Bruton Jr. Centennial Professor of Computer Science at the University of Texas at Austin. Scott recently moved to Austin. Prior to that, he was a professor at MIT for many years. I believe, Scott, you and I have met physically in the real world, meet space world a few times. I think maybe at SciFu at the Googleplex.
Oh, okay.
And also, I definitely remember at one of the Microsoft Research Summer meetings, you and I were both there, and we took some cruise around the Seattle Bay or whatever it is.
Oh, sure. Okay.
Yeah. So anyway, we've met before,
Mhm.
and obviously, I've been a long reader of your blog. So I'm super excited to have you here.
Yeah. Well, thanks for having me. It's great to be here.
Great. So what I'd like to do is start with a little bit about your background, your education. I think you were famously a very precocious kid. Just want to understand how you came to mathematics and then how you came to the particular research specialization that you've chosen. So maybe just tell us a little bit about your childhood.
Okay. I like math for as long as I can remember, really. Seeing how rapidly, the powers of two increased, with a calculator, when I was 4 or 5, that I remember that. I mean, I remember it just completely rocking my world. And learning what negative numbers are, and then it was a very big deal to get a scientific calculator that had these buttons like sin and cos that like, what the hell are these, right? Well, what do these do, right? And and then that was just another mystery that one had to get to the bottom of. But I think that my goal for a while was actually to create my own video games, like many kids, in the 1980s. I got a Nintendo set and got obsessed with Nintendo, right? But what I really wanted to was to create my own video games. I would just spend hours and hours just thinking about it, thinking about how I would design the game. Would it be a three-dimensional? What would the levels be like? Right. But I had no clue what it would take to actually bring any of it to life. I mean, that was just, a complete black box for me. That was a mystery. Maybe, you need a giant factory to involve the components. Right. So I think that it was one of the most revelatory moments in my life was, this would have been when I was 11 and I was at a friend's house. He had just and I'm not even a Mac. I think an Apple II. He said, do you want to try messing around with BASIC? I said, what's BASIC? And he said, well, it's a language. You can write programs with it. Like, so for example, here's a game. It was the some simple thing, either Pong or so, a worm crawling around and growing. Right now, here's the code of the game. Right now, you can change this code here, like right here, and the game will do something different. Right. And I've said that for me, that was kind of like learning where babies come from. Right. It's like, the fact that you could take these whole worlds in miniature, these, video games, and the creation of them is they're reducible to a math problem in some sense. It's just, reducible to writing this code, right? Which is not just some kind of summary of the game, but is the game. And so then, I had to learn what programming was. I mean, I think my parents say that I had a tantrum. I was crying that sort of that they didn't tell me about this earlier, right? And that other kids might, have a head start on me that I would never be able to make up at this point, right? And I learned what I could about programming in the next few years. But then at some point, I think I ran into a wall, and you could say that was about at the precise point where programming turns into software engineering. Right. So, I loved, writing little programs for myself that would just test things like, you know, for example, if you have a little worm that grows on the screen in random directions by taking a random walk, but it can't revisit any squares where it's been before. So it only, picks a random square among the ones that it hasn't yet visited, right? Well, eventually it will get stuck. It will be, surrounded on all sides by squares that it's visited. How long does it take until that happens? Hey, it turns out that it's about 70 steps. Right. And, I remember just leaving my computer on all night, to answer that question. I just spent years doing that kind of thing. But then I then met other kids, when I was 12, 13, I met another kid at my school who was actually writing shareware games, who was putting them on America Online where people could download them and play them. And that guy, he became a lifelong best friend of mine. He's now a well-known computer security researcher. His name is Alex Halterman, right? But, maybe I didn't realize quite how extraordinary he was. I thought, wow, other kids are just such better programmers than I am, right? And in particular, once I saw that to actually write significant software, right, it involves documenting your code so other people can read it. It involves meeting deadlines. It involves getting your code to interoperate with everyone else's code, right? And I realized that other people were just much better at that stuff than I was, right? And if I had any comparative advantage, then maybe it was more on the mathematical side. And so I think that's probably what drew me more into the theoretical part of computer science. I mean, when I was 13 or 14 or so, I would have been reading, and just learning about what is big O notation. How do you analyze algorithms, right? That there could be an obvious way to solve something, but that's not the best way, right? You can be cleverer about how you organize information, and then I would have learned about the P versus NP problem. Actually, when I was 15, I went to a Canada USA math camp in Seattle, which blew my mind at the time, right? Because I mean, from being in high school to sort of being directly taught by these amazing mathematicians, right? Suddenly I was struggling to keep up, right? And I was at best somewhere in the middle. But in particular, Richard Karp was there. Richard Karp was one of the founders of the theory of NP completeness, and he gave a series of lectures about how to prove things are NP complete, about non-trivial efficient algorithms, and that had a very big impact on me. And, I probably had fantasies, when I was 15 that, well, I was going to solve the P versus NP problem, right? And just, it must be just some simple idea that everyone's been overlooking, and I think, it's important for someone learning a new subject to sort of go through that stage, to be burned by it, as it were, right? And emerge a little bit wiser.
Someday some kid will foolishly think he can prove P equals and actually do it, right? Let me just jump in for a second because I want to
Yeah,
come back to
yeah.
talk about more about computational complexity and whether P. But I just want to remark that this is I'm learning all kinds of stuff about you that's fascinating. So you were already thinking about computational complexity. You even knew about big O, little o notation. And then you went to this math camp, and then you met one of the leading people in the field. So that was
Mhm,
extremely fortuitous, right?
mhm, mhm,
And so when you went to college, you went to Cornell,
mhm,
is that right?
mhm.
Were you already
Yes. Okay, so there's a weird story, right? I mean, when I was 13, I lived in Hong Kong for a year because my dad was working there, and I went to an American, international school, and I had always been, ahead in math or, doing something special in math, and this school couldn't accommodate it except by letting me skip to ninth grade, and so after a lot of discussion, they finally, gave me permission to do that. And that was kind of like a dam breaking when, like, I realized, wait, you can do that. You because, I'd been, very unhappy in junior high school. I felt like I didn't belong, and I felt like maybe if I can get to college, that will be in an environment where I'm happier. And I think at that point, my goal became to just sort of get to college as quickly as I could. And so we came back to the US after that, and somehow I finagled my way into being in 10th grade, but 11th grade. And I took AP calculus at that point, and, and then there was no more math to take. And so my parents suggested that, well, why don't I just do multivariable calculus and differential equations as a self-study? And the school vetoed that. They said, I'm not allowed to do that. And so then I sort of seized on that as my excuse to sort of get out of high school. And I found out at this point about a program at Clarkson University in upstate New York, which is called the Clarkson School. This is a program where high school seniors can live, in Potsdam, New York, at Clarkson University and take college courses for the year. And I said I would like to do this. And because of the math thing, I sort of had the pretext for being able to do it. And so I went there and I had an amazing year. This was the summer after the math camp, and I actually found a professor at Clarkson named Chris Lynch, who I was able to work with. And at that time, the web was fairly new. I had an idea for how you could sort of optimize the design of a website with, like, a limited budget of links. And so I wrote my first paper about it. That was this year that I spent at Clarkson. And from there, you could apply to colleges as a freshman. I applied to all the usual places. I was rejected almost everywhere I applied. I guess, because my background was too bizarre at that point. But Cornell was nice enough to accept me. And so then that is how I ended up going to Cornell the year after that. That would have been when I was 16. There was one problem before I could start at Cornell, which was that, they required a high school diploma. And I did not have one. Sometimes one's old high school is sort of nice enough to give you a diploma after you go to Clarkson school, but my high school said, "Well, no, I am missing phys ed, so I have to spend the whole summer doing push-ups, basically, if I want a high school degree." So instead of that, he said, "Well, what about getting a New York State GED?" Okay, and so then you had to be 17 years old to get a GED, which I wasn't, but my mom spent hours on the phone with them, and I got them to agree to give me a GED. So then, that I actually had that GED hanging in my office when I was teaching at MIT for 9 years. That was my
Now, was the actual crucial event that you had to walk into some room at Cornell and show them your GED? I mean, is that how
no, I don't think it was that dramatic. It was just something had to be mailed. I think it was just becoming electronic at that point in time. We were still mailing things around.
right. But at this time, you sort of knew you were interested in theoretical computer science. Is that right?
Yeah, well, I was interested in theoretical computer science, but I was also very interested in AI. And actually, when I was at Cornell, it was really the AI people who I ended up working with more, especially a professor at Cornell named Bart Selman, who's a leader in AI and in sort of trying to solve NP complete problems in practice, not just theoretically, right? Sort of in the empirical study of NP complete problems. And I became a sort of protege of his. And, he was also the advisor to Cornell's RoboCup team. RoboCup is this robot soccer league. And so I spent a couple of years working on the AI programming for Cornell's robot soccer team. In one sense, that was very successful. And, we won the world championship for 2 years, but that was also, I think, an experience that clinched for me that I should not be a software engineer, right? Because just, having to write all this code, meet all these deadlines, have all of these other people depend on me, right? It was just sort of nightmarish for me, right? They would have some idea for how the goalie could work, and I would be like, "Well, maybe we can prove that that's actually NP complete. Let me spend a few weeks to think about that, and then, maybe after a few weeks, hey, I can prove it." And they're like, "Yeah, we don't care. We're doing it a completely different way now anyway." So these were some of the experiences that sort of pushed me into theory, right? But, there remained the question, as certainly at that point of, can I do anything new in theoretical computer science? Because As I said, I thought about things, right? But, let's say, but by this point, my ambitions had scaled back from, solving the P versus NP problem, right? But even to do a much more modest thing, again and again, I had the experience that, you try to do something new, and then, either you fail or else you succeed. And then it turns out that it was already known. Uh, and so I really wasn't sure if I could do anything new in a field like that. And then, when it came time to apply to graduate school, it was actually the AI people who took more interest in me than theoretical computer science people. So I did much better with graduate school than with undergraduate admissions, and I had a lot of great choices, and I ended up going to UC Berkeley for my PhD. Right, but it was actually a machine learning person, Mike Jordan, who was the one who recruited me there. And, and at the time I thought, well, maybe I should do that. I mean, machine learning seems like, an up and coming field. Maybe that's going somewhere. Right.
Yeah.
And that this would have been in 2000. And I spent a year doing that. But at that point, I think my heart was secretly in quantum computation. And that was really a thing that I was curious about. And maybe, the leading theoretical computer scientist working in quantum computing named Umesh Vazirani was there at Berkeley in the CS department. And my dream was really to work with him. And it took a year for me to sort of work my way into his group, but that's where I ended up. And that was 21 years ago. And I guess I'm still here doing quantum computation.
Can I ask you a little bit about that? So,
Really?
my familiarity with quantum computing is mainly from the theoretical physics side.
Hmm.
And so to me, Vazirani is kind of a mysterious guy because
Yeah.
he's from this different community, but
Mhm.
has, done important work. And so I was always curious, how did the theoretical computer science community first get interested in quantum computing? Because I think probably some aspects of quantum mechanics must be very novel to them or unusual. Or
Yes.
maybe they just thought, okay, once you reduce it to a set of unitary operations, it's sort of something we're used to. Yeah.
Yeah, no, it's an excellent question. I think in the 80s, quantum computing was not yet a field, right? It was an idea that a few physicists had explored, famously Richard Feynman and David Deutsch. And then they sort of realized that there was this theoretical computer science question here. If you're trying to simulate a quantum mechanical system, then is there any way to sort of avoid this exponential explosion, in the size of your state, in the number of amplitudes, that seems to be inherent when you try to represent a quantum state with a classical computer. But that was only one thing of many that they were interested in at that time, right? I wouldn't say that they really focused in on it as the central issue. Only, in the early 1990s, I think that a few computer scientists, started getting interested. So Charlie Bennett was a very important figure here, right? So, Bennett was trained in physics and chemistry, but, was also did a lot of important work in computer science. Also, Gilles Broussard, who was Bennett's friend and collaborator, they invented the BB-84 quantum cryptography scheme together. So, there was this small community of people who were making these connections between physics and computation. So Umesh Vazirani, has told me, basically, once he got tenure at Berkeley, he was just looking around for something new and different to do. And, he read Feynman's paper about quantum computation, and he decided that this was it. Right. So he and his then student, Ethan Bernstein, wrote a now seminal paper in 1993, which was called Quantum Complexity Theory. And this was the first paper that really systematically studied quantum computing, from the standpoint of theoretical computer science. Okay, so what they did is they said, well, what is the right quantum mechanical generalization of the class P? Right, P is polynomial time. It's the class of all the yes or no problems that we think of as efficiently solvable by a Turing machine, by a conventional computer. So, for example, given given a graph, is it connected? Is every point reachable from every other? Or given an integer written in binary, is it prime? Okay, these are examples of problems in B. So Bernstein and Vazirani defined a class that they called BQP, bounded error quantum polynomial time, which was like a generalization of P, where now, you're allowed to do unitary transformations. You have qubits instead of bits, and you have to, at the end, a measurement gets made of the quantum state. And this has to lead to your, getting the right answer to your decision problem with a high probability. Okay. And again, we impose a requirement of efficiency. So, the number of elementary operations, quantum gates, we would call them, has to be bounded by some polynomial function of the size of the problem that you're trying to solve. And so they sort of, for the first time, they systematically studied, well, what is this BQP? Is it at least, as large as classical P? Okay, so they, verified that yes, it is. Could it be just infinitely powerful, right? Could quantum computers let you solve, the halting problem or, uncomputable problems? Well, no, it doesn't go that far, right? So, anything that's in quantum polynomial time is also in classical exponential time. Okay, so, and this is basically because with a classical computer, you always can simulate quantum mechanics by just writing down the entire wave function, right? The entire quantum state. But then, they could show something better than that. Actually, anything that you can do in quantum polynomial time can also be done by a classical computer with polynomial space, with a polynomial amount of memory. And for a physicist, I would say the reason for that is basically the Feynman path integral, right? It's that you can take the probability of an outcome that you care about and just represent it as a sum of exponentially many contributions that could be positive or negative. And then you can just evaluate that sum, needing exponential time, but reusing the same memory. And so then that already told you something very important. It said that in the present state of computer science, there is basically no hope of proving that BQP is larger than P.
Mhm.
Right. Okay. Right. So, because like the obvious question is, well, can a quantum computer do something efficiently that a classical computer cannot? Okay. But this said that, well, sorry, if you want to prove that as a theorem, then you would also have to prove that P is not equal to P space, because this BQP is sandwiched in between P and P space. Okay, but to prove P is not equal to P space is considered essentially as hard as proving P is not equal to NP. Okay, right. This is one of the great unsolved problems, right? So quantum computing people have a good excuse for
Mhm.
our failure to solve this problem. It's not our fault, right? But now, the next question that they looked at was, well, can we at least give some evidence that BQP is larger than P? And they gave what is known in the trade as oracle evidence or black box evidence. Okay, they said, if you imagine that we had a certain black box that we can make queries to, we can ask it questions, but we don't know its inner workings, then we can design a black box that would cause BQP to be larger than P. Okay. So this doesn't answer the question in the real world, as it were, but it says that, there is some hypothetical black box that would make quantum computing more powerful. And now it says, if you can just find a sort of real problem that instantiates that black box that gives rise to the same sort of behavior, then that would give you an example where quantum computing really was more powerful than classical computing. And so the Bernstein Vazirani paper kind of, set off this chain reaction of later, of events over the next year or two, where what happened was, first someone named Dan Simon read their paper and said, well, this doesn't sound right. I don't think that quantum computers should really get such an interesting advantage, and tried to prove, the sort of Bernstein-Vazirani separation was limited, and ended up proving the opposite. Ended up proving that actually, a much better separation is possible. not just more than polynomial, but actually exponential. And for another black box problem, which was called Simon's problem. So Simon wrote a paper about that, submitted it to one of the premier conferences of theoretical computer science, and it was rejected. Okay, people just didn't know what to make of it, or they said, maybe it involves this fanciful black box. Like come back to us when you can say something about the real world, right? But there was one person on the program committee of that conference who said, no, I actually think this paper is interesting. And that person was Peter Shor. Okay. And what Peter Shor said was that, what Simon's quantum algorithm was doing is, it's kind of like identifying a hidden periodic structure in a function. So like you're given a black box, it computes a function that has this sort of hidden global behavior to it, where a classical algorithm would need an exponential number of accesses to the black box until it had figured out the pattern, until it figured out this sort of global symmetry that the function has. But he showed that if you could evaluate all possible inputs to this function in quantum superposition, then you can sort of arrange a pattern of interference that reveals the answer in only a polynomial amount of time. And then Shor said our cryptography, that we protect internet commerce by, and then that itself was just really starting at that time. This was 1994, right? But, RSA and Diffie-Hellman, right, our forms of encryption are also based on functions that have sort of hidden periodic structures. What if you could just change Simon's problem around a little bit in order to find the periods of those functions, of integer functions? Wouldn't that then let you factor numbers efficiently and calculate discrete logarithms efficiently, things like that? So that turned out to be technically much more involved than what Simon had done. And Shor had to work on that for a year, but he eventually found that it was possible. And that's what we now know is Shor's algorithm in 1994. Now Shor was a mathematician, but one who had also studied physics. I should say that Vazirani was a computer scientist, but who had also studied physics, right? So they had kind of the right combination of training to be able to make these connections. And once Shor announced his factoring algorithm, that was when the floodgates opened. And, I think people realized that, quantum computing was going to be a thing. It was not going away. And, immediately they started trying to figure out two more things, which 28 years later are still at the center of our interest. And the first thing was, well, what else is a quantum computer good for? Right. Supposing that you have one, supposing that it works perfectly, what else can it do besides factoring numbers or these few other very special problems? Right. What about for NP complete problems? How much of an advantage does a quantum computer give you there? Right. Even if P is not equal to NP, is it possible that quantum mechanics makes a difference there? Okay, we're still studying that question, decades later. And then the second, maybe even more obvious question is, well, how do you actually build a quantum computer? How do you take this theory and how do you turn it into engineering? And that led to another great development in the 1990s, which was the theory of quantum error correction, quantum fault tolerance, which said, how can you make this work not with ideal perfect qubits, but even with noisy qubits, which is what you have in the real world. People had amazing theoretical ideas about that in the 90s, including Peter Shor himself, by the way. And decades later, they are finally starting to turn those ideas into reality, just about now. So, so all of this was happening in like 1994, 95, when I would have been 13 or 14 years old. Uh, I was not, aware of it at the time, but then I would say around 95, so maybe a year or two after it had all happened, I read a popular article about it, about Shor's algorithm and so forth. And my first reaction when I learned about it was, this sounds like obvious garbage. This sounds like some physicists who just sort of stumbled into computer science and, think that they can solve exponentially hard problems and just do not understand the enormity of what they are up against. Right. And, and I should say, this skeptical reaction, was shared by many computer scientists. There are some who still have that reaction, right? Who haven't gotten over that reaction. And it is an attitude that actually has a lot of support in the history of computing, right? Again and again, people have tried to design architectures, analog computing, for example, that would get around the limitations of the Turing machine. And again, they failed, right? Because they were always ignoring some resource that would actually blow up exponentially, such as the energy that you would need or the precision that you would need in measurement. Okay. And so, you could say a natural first guess would be that quantum computing would just be another example of the same thing where people are just sort of ignoring some resource that will blow up on you and become exponential when you try to actually build one of these quantum computers. But then, I sort of had no choice but to learn more about, right? Because, like I didn't think of myself as a physicist at all, right? I'm a math computer science person, but it's like now physics is impinging on our world. Right. It is making this, enormous claim about, the world of P and NP that, I have to see if it's true. So when I was at Cornell, I was lucky enough to be able to do a couple of summer internships at Bell Labs. This was when Bell Labs was still I guess,
Did you meet Grover when you were at Bell Labs?
I did. So, yeah, so first I worked with someone named Eric Gross just on some statistical software. It had nothing to do with quantum computing, but I got really curious just, reading about Shor's and Grover's algorithms, how they were, and there were already web pages about it. The web itself was only 5 or 6 years old. I read about these quantum algorithms, and I was blown away by a couple of things. First of all, that I could actually understand this, right? I would have imagined that. Well, I would have had to study, physics for years and years before I could even begin to understand what they were talking about. But then when you actually go and read the papers, it's like, oh, it's just your state is this unit vector of complex numbers. The way that you act on it is by unitary matrices, just like you were saying before, Steve. Right? It's kind of like a classical probabilistic computer, except that instead of probabilities, which are real numbers between 0 and 1, now we have these complex numbers, which are called amplitudes. So, okay, that's very interesting. I think even if our universe had been classical, someday some computer scientist could have defined BQP,
Mhm.
right?
Yep.
Just for purely theoretical interest, and it would have been an interesting thing to study, right? Of course, the fact that our universe really does run on these amplitudes, that does heighten the interest of this, to put it mildly. Okay. But this was really just linear algebra, right? And, I knew linear algebra, right? And, at that point, I didn't know what a boson was, what a fermion was, what a Hamiltonian was, right? Creation operator, and I didn't need to know any of that, right? I could, learn all the details of how the quantum algorithms worked, just by learning these rules, these abstract rules of unitary evolution and measurement. It's very similar to how, you could learn all about programming, become a virtuoso computer scientist without needing to know how a transistor works. Or in principle, even that there is such a thing as a transistor, right?
Yep.
It's all been abstracted away for you. And I saw that something similar was true in quantum computing. And so I learned about it, and my boss, Eric, was kind enough to say, "Well, why don't you just spend a few weeks just learning this subject?" And so I did, and I even managed to prove some, I was very excited to prove some new results, but then, it turned out that those results were already known. Okay, but, it wasn't that like I was reproving stuff that was like 50 years old. was that I was reproving stuff that was 1 year old.
Hmm.
So, like someone had beaten me to it by 1 year, right? And then I found out that Lava Grover worked in the same building at Bell Labs as I did, right? And now Grover was the discoverer just a couple of years before of Grover's algorithm, which is maybe the second most famous quantum algorithm after Shor's factoring algorithm. Okay, so compared to Shor's algorithm, Grover's algorithm has an enormously greater range of application. It works for NP complete problems. It works for pretty much any combinatorial search or optimization problem, that you could think of. It's been generalized to other stuff like playing games like chess or Go, Monte Carlo estimation, machine learning problems. But the disadvantage is that the speed up from Grover's algorithm is not exponential, right? It is quote unquote only quadratic. So like where a classical computer would need n time, Grover's algorithm needs the square root of n time.
Can I ask you about that? So in the case of Grover, we know very well that it's n goes to square root of n speed up. In the case of discrete logs and factoring, do we really actually know what the optimal classical performance would be on those problems? Because
Well, no, absolutely not. This comes right back to, these central mysteries of theoretical computer science that we were talking about before, like the P versus NP problem, right? If P were equal to NP, then among many other things, it would mean that there was a fast classical algorithm for factoring numbers, and it would mean that Shor's algorithm does not achieve an exponential speed, right? So,
but even sorry to interrupt, but even if P is not NP,
mhm,
isn't it true that the exact polynomial scaling of the
mhm.
difficulty of factoring is not really known? Is that true?
That is also true.
Yeah.
That is true as well. Yeah. So factoring seems to inhabit like a twilight zone between P and the NP complete problems, right? We do not think that factoring is NP complete. We have excellent theoretical reasons why it shouldn't be, but then on the other hand, we also don't have a fast classical algorithm for it. Okay, so it seems to have a lot of special structure, and that special structure was enough for sure to design a quantum algorithm to solve it. What we don't know is whether it's also enough to design a fast classical algorithm, right? Now that there are classical algorithms for factoring that do better than pure brute force. Okay, the most famous of these is called the number field sieve. Okay, so it lets you factor an n-digit number in time that is instead of exponential in n, it's roughly exponential in the cube root of n, right? This is using elliptic curves, but this is how, presumably, the NSA or the GCHQ, right, when they are attacking people's cryptography, they're presumably using algorithms like these. And there's some evidence, from the Edward Snowden documents in, 2014 that at least at the time they were doing something like that. But you've put your finger on, one of the central difficulties of this field, which is that, we don't know in present how to prove inherent limitations of algorithms in most of the cases that we care about. So we can say, there is an algorithm to do such and such, but, is it optimal? We don't know. People still wonder, well, how great of a speed up can quantum computers give for solving NP complete problems? Now, what we know is that there's this thing that I was talking about before called the black box setting. The black box setting is where you sort of abstract away all the details of the problem. So you could say, imagine that we just have this abstract function that lets you search in a haystack. You tell it where you're searching, and then it tells you if you have found the needle in the haystack or not. Right. And then in that setting, we know that Grover's algorithm is the best that even a quantum computer can do. Okay. And so that's a very important theorem that was proven by Bennett, Bernstein, Broussard, and Vazirani in 1994. It's called the BBBV theorem. And ironically, this was proven before Grover's algorithm was even discovered. Okay, so Grover's algorithm was proved to be optimal in the black box setting before it was even discovered to exist. And I think at the time they said, well, we can only prove that square root of n steps are needed. And presumably that's just some technical defect in the proof.
Hmm.
And then Grover came along a year later and said, no, it's not a technical defect. That's because, there is as we would say, a matching upper bound, right? A quantum computer really can solve this abstract search problem in square root of n time. Now, the trouble is, that still doesn't answer what you might really want to know in practice, which is, well, let's say you have the traveling salesman problem, right? Or you have satisfying a bunch of constraints for some, model checking for some, microchip design or some machine learning problem, or you're trying to break some cryptographic code, or you're trying to mine new bitcoins or something like that, right? These are all problems that are not just purely abstract search problems, right? They have more structure to them. And so then the question remains, well, could a quantum computer exploit that structure to do better? This we don't know. In formal terms, this is the question of, is NP, which is the class of all the problems where a classical computer can at least verify the answer efficiently when given it, is NP contained in PQP? Can NP complete problems be solved in polynomial time? Then, maybe not surprisingly, we don't know the answer to that, because we don't even know whether NP is contained in P,
Hmm.
right? But we know that if there is a fast quantum algorithm for NP complete problems, then it has to look very, very different from any of the quantum algorithms that we currently know. It has to look very different from Grover's algorithm, which only gives you this square root speed up. It also has to look very different from Shor's algorithm, which requires this very special structure, this periodicity structure, which the NP complete problems don't seem to have. So, there's now been like almost 25 years of efforts to, work on that problem, often by designing heuristics. So, people have studied, what about annealing processes, right? There's something called the adiabatic algorithm. And these are kind of like, you take classical heuristic methods, that are, like simulated annealing, which are not guaranteed to work. They can take exponential time, but often enough, they give you a good solution in practice, and you can sort of make them quantum, right? You can try to take advantage also of quantum tunneling effects to sort of get out of local optima and get to the global optima. Okay, and this is exactly what people study with this quantum adiabatic algorithm. Okay, but after more than 20 years of research on it, we still don't really know. Sort of, is there some subset of optimization problems that matters in practice where, this will give you an exponential speed up over classical algorithms? We know that you can, in this black box scenario, we now know as of the last year or two, thanks to a breakthrough by Matt Hastings and subsequent work by Umesh Vazirani and Andres Gillian, we know that you can construct solution landscapes where any classical algorithm needs exponential time, but this sort of quantum annealing approach will reach a global optimum in polynomial time. So that's possible, but then are these landscapes ever relevant? Do they ever arise in any practical optimization problem? That we still don't know. Okay. So, there's plenty on our plates, even just on the theoretical side of quantum computing, even today. Right. And this is one of the examples.
I think that was a great introduction to, an area for people like me who, if you come from the physics side and you read some textbook on quantum computing, all the computational complexity stuff is in some kind of overview chapter at the beginning. And
Yeah. Right. Right. Exactly. Right. It kind of gets.
you see some Venn diagram with BQP and
Yeah.
these.
Yeah. Right. It all gets shunted off to the side. Yeah. Steve, you got to look at the Bernstein Vazirani paper. Yeah.
I think I did look at it in the 90s without understanding it at all, right? So,
It does do everything, and from today's standpoint, is like a ridiculously unwieldy way, right? Like, we could say everything much simpler today. So maybe look at my lecture notes. Look at my, so anyway, I was about to say, I ended up working, I met Grover, I told him my ideas for Grover's algorithm, and how to improve it, which were complete nonsense, right? Which just didn't work at all. But Grover was kind enough to offer me an internship with him the following summer at Bell Labs. And So I did that, and I met some of Vazirani's students from Berkeley were also working with Grover. So I met them and I learned actually what was, the state of the art in quantum algorithms research. And that's when I sort of formed the intention, like I have to go to Berkeley. I have to learn whatever it is that these people know. And so that was really how I got started in quantum computing research was really, that summer at Bell Labs.
After all that, it's kind of amazing that you spent that year with Michael Jordan in ML.
Yeah, yeah. Well, I had an idea at the time that maybe I'm going to combine quantum computing with machine learning,
Right.
how come no one's talking about that, right?
Yeah.
At the time that no one was talking about it, so I needn't have worried, right? Like, if I just gave it another 10 or 15 years, that would become like, the most hyped thing in the history of hype, right? And, which is what it is now.
Yeah, it's like hype squared, and then if you can add crypto into it, you're done.
Exactly, exactly. But, I was thinking about that even in, 2000, but then, decided, well, yeah, I can invent quantum versions of all these machine learning concepts like graphical models and so on. But then what do you do next? Right? Why is this useful? How do you show that there is an advantage compared to the classical versions of these things? And since I couldn't answer those questions, I sort of set it to the side. Now, if I had only known from today's perspective, right, I would have known that none of that is any barrier at all. You just write hundreds of papers about it anyway.
Yeah. But I'm a little worried that we might have lost some of the listeners who are not so theoretical in
Mm,
their orientation. So maybe we can switch to a more concrete topic, or at least one that's in the news, which is quantum supremacy.
okay.
So maybe we can explain, because I'm sure people see these headlines all the time, right, on the
Mhm.
internet that,
Yeah.
oh, they've got this quantum computer now, which is, better than any classical computer we can possibly imagine.
Yeah.
Maybe you could just say what you think about quantum supremacy and what's a useful way to think about it.
Yeah, sure. So the term quantum supremacy was coined by John Preskill a decade ago, although it referred to something that some of us had been thinking about for several years by that time. And it's basically just how do you use a quantum computer to do something that we're as confident as possible is hard to simulate with a classical computer. And now it is crucial that I did not say something useful. Okay. It could be some completely artificial benchmark. But, our goal is just to sort of prove the quantum computing skeptics wrong. Kind of like, the Wright brothers airplane was not, useful for commercial air travel, right? It existed just to prove a point. So around 2010, 2011, some of us started thinking about, well, how do you use a quantum computer, which might not be ideal, not quite what we want. So it doesn't have thousands of perfect qubits. Maybe it only has 100 noisy qubits, right? But can we still use it to do something that would sort of demonstrate the reality of exponential speedups by means of quantum computation? We realized that there are a lot of advantages to switching attention from problems like factoring that have just a single right answer to what are called sampling problems. Okay, a sampling problem says, I'm going to describe to you some probability distribution over some huge number of possible outputs. And now you just have to sample a random output, but consistently with that distribution. So the pattern of which outputs are likelier or unlikelier, should match this distribution. So around 2011, my then student, Alex Arkhipov, and I came up with one of the first proposals for how to do this, which we called boson sampling. At this point, I did have to learn a little bit more physics. I did have to learn at least what bosons were. Although at that time, it was still for just a sort of a theoretical computer science reason. We wanted a quantum computer to sample from some distribution in which the probabilities were given by very, very hard functions for a classical computer to keep track of. And we focused on a particular hard function, which is called the permanent of a matrix. And this is, so a lot is known about the permanent from the standpoint of computational complexity, that it's something called sharp P complete, which we think is even harder than NP complete. And so we thought that it had the right properties for creating one of these hard sampling problems. But then we needed to know what kind of quantum computation would give rise to permanence as the amplitudes. And the answer turned out to be a quantum computation based on bosons, based on generating a bunch of identical bosons, such as photons, for example, and then sending them through a network of beam splitters, for example. And then you would have to sum over sort of all possible ways of permuting these identical particles around, and each way of permuting them would make another contribution to the amplitude, and you'd get a permanent. I had known that that connection existed for a long time, but I never really knew what to do with it. And so we decided, well, could you use this to just create some very, very rudimentary quantum computation, but that nevertheless we can give evidence is hard to simulate with a classical computer. So that's what we did. We published about that in 2011. And then what happened, and I should say other people, Bremner, Jose, and Shepard, came to very similar ideas, but not from bosons, from different starting points. And then the experimentalists around that time got all excited, right? Because they said, well, guess what? These bosons are not just a theoretical construct. We have photon sources in our labs, right? We do stuff like this all the time, right? We send photons through networks of beam splitters. We send them into photodetectors and we measure where they landed. Maybe we could actually do this. And that was really a new thing in my career, because I had been about as far as you could get on the theoretical end of quantum computing research for a decade. Occasionally, like, I would be let into a lab for a lab tour, if I promised not to touch anything, right? But it's like, I didn't know, like, they could have told me that their coffee machine was the dilution fridge, and I probably would have believed them. Okay. But once the quantum optics people started getting interested in boson sampling, then we realized, wow, we are actually going to be collaborating or, working with experimentalists now to try to make this a reality. And so then Preskill wrote this paper where he gave the name quantum supremacy to sort of this quest to sort of, demonstrate a quantum speed up for something. It doesn't have to be something useful. And then there was a backlash. Not everyone liked that name, and so today people are calling it quantum advantage.
Oh, yeah, it's not politically correct, supremacy.
Exactly. But
Can I just can I just ask though, is the definition of it, do you allow the classical computer to work for the age of the universe, or what is the actual, at what point do you actually state?
to my mind, the definition is, you want a well-defined task. So you can specify in advance, what the inputs and outputs are, right? And so I want to rule out, you say simulate this system, right? That's not a precise enough definition of a task, right? I want a mathematical specification of what is to be done, such that it would make sense to say, did the quantum computer fail to do that task? No
Mhm.
machine ever fails at the task of simulating itself, right? But a device could fail at the task of boson sampling, from a certain distribution. So now what we say is that the quantum computer should be able to do this task in a reasonable amount of time. We should be able to verify that it really did do the task. But with a classical computer, it should take us orders of magnitude longer to do the same task. And it has to be a competitive process, right? The classical skeptics need to know all the specs of, what they would have to do to match this. And they have to have worked on it for at least, a year or two, put a real effort into it, and just not be able to come within several orders of magnitude of matching the performance. So, there are still many details that you can quibble with. And
Yeah.
actually, the people have been quibbling about over the last few years, right? What exactly counts as quantum supremacy? How exactly do you measure resources, right? What if a quantum computer can do something and then you can match its performance using, an enormous network of, thousands of cores with a classical? Yeah. Do you say that a quantum advantage remains? You would like to say maybe, yes, it does. You could say, even when there's not a quantum advantage in time, maybe there's a quantum advantage in carbon
Right.
footprint. You know, right? You're using massively more energy to run this classical simulation than you are to run the quantum computer itself, even though the quantum computer needs a dilution refrigerator and so forth, so it's not exactly a energy friendly thing itself. Now you could say ideally what you would want is like a much, much larger separation. You'd like something that a quantum computer can do in a few minutes, and that, with the largest classical computers on Earth would take millions of years or billions of years, right? And we hope that eventually Shor's algorithm will get us to that point, of doing that kind of demonstration. But with the existing quantum supremacy experiments, there's a difficulty which fundamentally prevents us from showing a separation that's that large. And the difficulty is, well, we still need a classical computer to verify the answer,
Hmm.
right? We need to prove that the quantum computer did what it's supposed to do. And with boson sampling, or with that style of quantum supremacy experiments, no one has discovered how to verify the answer with a classical computer except by doing this exponentially hard computation. Okay. So what that means is that you can do a demonstration with 50 qubits or 60 qubits. Right? And then that's exactly what Google did a couple of years ago. A group at USTC in China did just within the last year. And then you can actually verify the results, using, let's say, a classical supercomputer, right? And it might take a week or a month, but you can do it. But, this inherently doesn't scale even to 100 qubits, because, you can do a 2 to the 50th power is within what you can do with the biggest classical computers on Earth. 2 to the 100 power is not. So really, new ideas are needed, right? I mean, the wonderful thing about factoring, the problem solved by Shor's algorithm,
Hmm.
is that it is easy to check the answer, right? Once, some machine has found the prime factors of some not, 1,000-digit number, well, then, you just, if you don't believe it, you just multiply those factors yourself. You just check. Uh, the trouble is that to implement Shor's algorithm, it seems to require an error corrected quantum computer. It seems to require something that we don't yet have. To do this error correction, you seem to need thousands of physical qubits to encode just a single logical qubit. Okay, so at that point, you would be talking about millions or hundreds of millions of physical qubits, and those of a higher quality than what we have today. There are now lots of companies that are sort of racing to try to achieve that, within the coming decades. And maybe they will, but that's not something that we have yet. Okay. And so quantum supremacy, what got people excited was that maybe you can demonstrate a quantum speed up even with a noisy device that is not error corrected. That's exactly what Google and USTC, have done or claimed to do or tried to do within the last couple of years. And it looks like a pretty clear quantum advantage remains in these experiments, but it is not as decisive as we would like, mainly because of this reason that I mentioned, the difficulty of classical verification, right? Which sort of puts a limit on sort of how far you can scale this stuff. So I think one of the great challenges for just the next 5 years is, can we figure out a way to demonstrate quantum supremacy on a near-term quantum computer? So, noisy quantum computers with little or no error correction, which is the kind of stuff that we've got now, but where a classical computer can easily recognize a right answer,
Right.
where you can easily verify it classically. And now for bonus points, you could try to do that also for a problem that is actually useful, right? That someone actually independently cares about. Okay. But I'm not even going to demand that part.
So just to make sure I understand, so the verification is a problem because it can be extremely hard for the classical computer. But in deciding that on this particular problem, it's a well-posed quantum advantage, you do have a rigorous limit on the best algorithm for the classical computer to generate the distribution in the first place.
Ah, okay. So that's another very good question. So yet again, it's going to depend on some unproved conjectures. Almost every hardness statement that you can ever care about in theoretical computer science, depends on some unproved conjecture. I hate to break this
But
to
is it
right?
a conjecture as that people are as confident in as say
Yeah,
P not equal NP?
that's an excellent question. Now, what got us excited about boson sampling a decade ago was precisely that we were able to prove a theorem that says that if you had a fast classical algorithm that could sample from exactly the same distribution that a an ideal version of this experiment, a noiseless version of this experiment would sample from, then that would have really dramatic consequences for classical complexity classes. I wouldn't quite mean P equaled NP, but it would mean that the polynomial hierarchy would collapse, which is something that complexity theorists tend to think would be sort of almost as shocking as P equaling NP.
Okay, but you're
Okay.
pretty
So we were able to relate the hardness of boson sampling for a classical computer to the non-collapse of the polynomial hierarchy. And Bremner, Jose, and Shepard reached similar conclusions about their model. Okay, and so that got people excited. Now, unfortunately, it still doesn't quite answer maybe the physically relevant question, because the problem is that in any real experiment has lots of noise in it. In fact, with these real experiments, when you make the measurement, you see about 99.8% noise, and you're just trying to extract, that tiny 0.2% of signal by repeating the sampling process several million times. That's what Google did. That's what USTC did. And so then that forces us to ask a new question, which is, well, what about the noisy version of the experiment? Is that also hard for a classical computer to simulate? And that we have not been able to relate to the non-collapse of the polynomial hierarchy. That remains one of the great theoretical open questions in this area, right? So Arkhipov and I, worked on it for half a year. We gave some evidence that sort of even the noisy version of boson sampling, we thought should be classically hard. Okay, but that remains an open question to give evidence for the hardness, that is at the same level of as what we know for the exact case of the problem. And then this is actually a very common pattern in theoretical computer science. So, for example, in cryptography, often people will design some cryptographic code, and they will prove a theorem that says, well, if you could break this protocol, this system, then you have to be able to, invert any one-way function, or sort of do something that would seem almost as dramatic as P equaling NP. And this is kind of the gold standard in our present state of knowledge, right? This is the kind of reduction argument that you want, right? I think theoretical computer science, to a large extent, is about passing the blame to someone else, right? It's saying, if my cryptographic protocol is broken, well, then it wasn't my fault, right? It's because these one-way functions were actually not one-way functions, or something like that. Okay, but then the trouble is when things actually get implemented in real life, then people always take shortcuts. But right, they always do things in the implementation, that sort of cut corners and that make it not exactly match the theoretical specification, right? And then, a lot of practical security research is just all about that gap. It's not about sort of breaking down the front door, breaking the underlying cryptographic code. It's about finding some side doors, right? Where just the implementation doesn't match the spec. And so we've seen exactly that same kind of dynamic play out with the quantum supremacy experiments, right? Where, in order to implement these experiments over the last few years, people have sort of cut corners, as it were. So they said, well, we don't have initial states that are just single photons, the way that Aaronson and Arkhipov wanted, right? We have what are called Gaussian states instead, right? We have, some percentage of the photons get lost on the way through the beam splitter network, right? Not all of the photons are detected at the other end. Okay, but we think maybe it's still okay, right? Or at least we still can't think of a fast way to simulate this with a classical computer. Okay, but then someone else comes along and says, aha, by using these imperfections in the real experiment, we can design a much faster way to simulate this with a classical computer. Yeah, and then the experimentalists go back and say, okay, but we can improve the experiment in order to rule out your attack. And then some other classical people come along and say, but we have a different attack. So then, that is basically the dynamic that we've been seeing over the last couple of years.
Yeah, I worry a related concern I've always had about error correction is that I think they use a
Mm.
fairly benign model of the noise that they're fighting. And I think they assume it's, pretty much uncorrelated noise that they have to beat down with
Mhm.
their error correction. And it could be in particular experimental setups, certainly that the situation's much worse than.
Yeah, I mean that's absolutely true, and that was recognized as an issue. I would say, from the very beginning. Once people proved these theorems in the '90s, about the possibility of quantum error correction, quantum fault tolerance, the skeptics of quantum computing knew if they want to say that this is fundamentally impossible, as opposed to merely hard, then either they're going to be denying quantum mechanics itself, or else they're going to be denying one or more of the assumptions that go into this quantum fault tolerance. So many of them have been doing the latter. They've been saying, well, what if the noise is correlated? What if it's sort of just conspiratorially designed to kill your quantum computation? And I think that that's a very important direction for research. But, we've learned several things since then. First of all, we've learned that even if there are correlations in the noise, as long as the correlations are small enough, like they fall off with distance, for example, then error correction should still work. But now the other thing is that, if you could really just design the noise with any correlations you want, and with complete advanced knowledge of which quantum computation is going to be applied. So like you're a demon, basically a quantum computer killing demon. Then, at that point, such a demon could also kill classical computation. And yet our classical computers work, right? So we seem to have some evidence that nature is not, malicious in that way. So Gil Kalai, the mathematician and one of the most prominent skeptics of quantum computing, so he keeps putting forward models of noise that to me are like that. They strike me as a conspiracy theory, on the part of
Yeah,
nature, right?
usually physicists are willing to assume that nature is not fighting against them.
Yes,
So
yes, exactly, right. Gill just sort of starts from the assumption that nature has to be killing quantum computing, and then he works backwards to sort of, well, then what could be true about the noise that would cause that to be true? But to me, the fact that someone as smart as Gill has not gotten any further, or has had such limited success in showing how, any natural noise model would do that is actually evidence for the opposite of his
yeah,
position,
I'm
right?
certainly nowhere near as worried about it as he is. That's
Yeah. No, but I could say something more, which is that the quantum supremacy experiments of the past couple of years have actually directly addressed some of these worries. So one of the most interesting things scientifically from Google's quantum supremacy experiment a couple of years ago is that they found that the amount of signal that they could sort of extract, by measuring their qubits, basically just went like the fidelity of each gate that they applied raised to the power of the number of gates. So just like the simplest, most naive thing possible, right? Basically, they saw the errors acting in a very uncorrelated way.
yeah, that's a good
Yeah,
sign.
yeah.
So, Scott, I'm conscious of the time. So we've been going for over an hour and 20 minutes, and I don't want to take up too much of your time. Maybe we could close with your thoughts. I read, I think, your recent blog post on DeepMind's Alpha Code,
Oh yeah.
and it reminded me because I thought most of our conversation would be about quantum computing, but it reminded me that you're a person whose opinion on I would really like to hear. And for example, whether recent progress has changed your priors or what your prediction is for human level AGI.
Yeah, well, I think that my opinion has changed over the last decade. I mean, I've been as astounded by the successes of deep learning as anyone else. Basically, I had not predicted that we would see this sort of just pure machine learning model that you tell it nothing about the game of Go, besides the rules, and then you just have it play against itself, millions of times, just completely ignoring all of the centuries of human expertise about how to play Go. And then it will just completely destroy all humans at playing Go, or for that matter, any other two-player game of perfect information, just about that anyone can think to design. And that the same approaches will work for voice recognition. They will work for translating text between languages. And now they'll work for generating programs that meet some specifications, right? I've been writing my blog since 2005 or so. And, so I was aware that, on the sort of nerd blogosphere, there were a lot of people worried about the prospects for AI taking over the world, right? And I interacted, even, 15 years ago with Robin Hanson, with Eliezer Yudkowsky, who were writing about these topics. And, I think I was mostly skeptical at that time. I didn't deny that it was possible in principle, but it just seemed like solving the problem of intelligence is going to be, this slog of who knows how many centuries or millennia to unravel this mystery. And that was partly informed by my own experience, having studied AI as an undergrad and as a beginning grad student, seeing just how enormous the gap often was between the hype and the reality, and just how little, these systems really understood, or just how brittle they were, to making slight changes to what kind of question you were asking them. But now, what the world has learned over the last decade or so is that if you just take the ideas that were already around in the 70s and 80s, just neural networks, back propagation. Now it's been rebranded as deep learning, right? But that's what it is, right? And maybe there have been a few new ideas since then. You have GANs, you have reinforcement learning, you have convolutional neural nets, but mostly you just scale it up to networks with billions of neurons, which of course people couldn't do back in the 80s, and you train them on these enormous amounts of data that you now have because of the internet, and then suddenly it works. It goes from not working to working. We still don't have a full theoretical understanding of why it works. Okay. And, there are many people who would, I have many colleagues who still kind of poo poo it. Right. And they say, okay, but these systems don't really understand anything. They're just pattern matching. It's just statistics. They're just regurgitating what you already told them. And they sort of seize on any evidence that maybe they're not working so well. Like, there's this whole subfield where you look for what are called adversarial examples, where like, if you know enough about how a neural network works, then you can design, a picture of, a pig that it will classify as a chicken. Like that, right? But then I look at that and I say, well, who is to say that if someone had the wiring diagram of my brain, that they couldn't design an adversarial example against me?
Oh, humans have been inventing adversarial tricks forever. I
What
guess.
are what are right? What are optical illusions, but a sort of adversarial example against us? So I think that the oath that we swear when we become scientists, right, is that like if reality tries as hard as it can to teach us a certain lesson, that we will learn the lesson rather than inventing clever reasons to maintain our previous worldview. Right. And I think that we do have to update on this, remarkable success that these methods have shown. Now, having said that, we don't know where it's going to go, right? I am still doubtful that you could take, let's say GPT-3, which is the text engine, and that you're just going to scale it up to, a few orders of magnitude more neurons. And then suddenly it's going to have desires and intentions, and it's going to rebel against its creators and take over the world, right? I don't think that that's going to happen, right? I think that, more likely it will just become better and better at sort of babbling, right? And what it does is, I think it has solved the problem of like generating essays that like could get a B or a C in an undergraduate class. It can sort of act like it knows about any topic, even though, on a close reading, really it doesn't. That is impressive in a way that an AI is able to do that. The thing that should make people nervous is that no one really knows, if there is a hard barrier between that and just completely solving the problem of intelligence, right? There might be a hard barrier, or it might just be that you need a few new tricks, maybe a lot more scaling to, bigger and bigger GPU clusters. And then what we are doing, what our brains are doing is just, some kind of pattern recognition that is fundamentally a lot like this. The people I mentioned before, like, Eliezer Yudkowsky, right? He has been famous for decades for arguing that the biggest task facing humanity right now is to ensure that when AI does, reach the level of super intelligence, when it starts surpassing us in intelligence, that it is aligned with our values, that it will sort of create a utopia for us rather than, wiping us out, maybe harvesting us for energy, like in the Matrix movie, or whatever, right? And, I am still, well, I guess if you look at how I voted with my feet, I am not spending my time working on that. I'm still, working on quantum computing and other things that are, interesting to me, right? And part of my difficulty is, well, even if I agreed in principle that, this is something that people should worry about, like, I'm still not sure what should be done about it as a practical matter,
Well,
right?
it,
Yeah.
I suspect that AI safety may be an unsolvable problem. I mean, it may be that
Mm.
even for us to predict the behavior of something superior to us may be not possible, and therefore to design it to guarantee safety could be quite difficult or maybe impossible.
Yeah, that is possible. I mean, Eliezer would say, well, we have to try because, that's our only hope as a species.
Yeah, I think it's fair.
Yeah, yeah. No, I mean, and I would also say that, just looking at the world today, problems caused by stupidity, by just greed and idiocy and sort of known flaws of humans are so severe that, maybe I would try my luck with super intelligence. You know, maybe it doesn't seem so bad by comparison, right?
Yeah, I mean, an argument I often make to these folks is that, probably the first few of these things are going to be very human-like. I
Mm.
mean, a lot of the intelligence they develop will be through looking at examples that
Mhm.
came from humanity, and even if they get rid of us, maybe by accident without noticing, they're still kind of like us. So they're like our, evolutionary descendants, and good
Yeah.
luck to them in the rest of the universe. Right? So,
Yeah, yeah, yeah. No, I mean, I think that is what they would say. They would, say, well, maybe to the extent that humanity will still exist, it will be because, we have uploaded ourselves or something, or we will have a very different form than
yeah.
what we have now. But, we want to make sure that whatever world is created that way, it's a world that we want, or, that we are happy to have created. And I mean, yes, the way that I would think about it is that, like, I hope that our civilization survives long enough for these to be, the most urgent
Yeah,
problems.
absolutely. I mean, it might be that decay wipes us out before we actually get the AI going.
Yeah, like there's so many mundane things. I mean, from, climate change to, to pandemics, as we're now suffering through, to nuclear proliferation, that I feel like if we can survive all of those things to the point where AI becomes sort of the most pressing concern, then, we will have done pretty well, right?
Yes. There's a science fiction novel called Void Star. I don't know if you've ever
I haven't.
Zachary Mason, who's actually trained
Okay.
in computer science. He has a PhD
Hmm.
in computer science. And
Mhm.
in Void Star, there's a job category in the future called AI Wrangler.
Hmm.
And because it turns out the AIs who live mostly in this they're first created in this virtual world, they're not interested in most things that humans are interested in. They're out trying to figure out whether P equals NP and doing all kinds of things in their own virtual worlds that to them are real. And so they immediately escape and they're living, in this massive worldwide network. And these
Mhm.
AI wranglers try to get them interested to solve some, material science problem or some mundane, how do we make our batteries better? Stuff that corporations care about. And mostly they just don't care about us. They're just doing their own thing in their own virtual universe. So
Yep. Yep. Yeah. I mean, it's true that, almost all of the science fiction that there's been about AI has just shown a sort of a staggering lack of imagination,
yep.
right? either they're, robot butlers or they're like, enslavers, like in the Matrix movie, but that can somehow be defeated by kickboxing them.
You see,
Right?
from, from my
And
perspective, Scott,
yeah.
you're a superhuman intelligence, but you seem to spend most of your time on benign pursuits, like figuring out whether P equals NP, right? So maybe,
Well, or just answering comments on my blog, or
yeah,
just dealing with my kids when they're, acting up. No, I am, I mean, look, I, look at, at Ed Witten or at Terry Tao, and I say, these are super intelligences, right? And I, because I am not that, maybe I can better contribute just by writing about science, or by, writing a blog, by, doing the various other things I do. No, I don't think of myself that way.
yes, I was kidding a little bit, but I just meant that the AIs might have
Yeah.
abstract pursuits that we can't understand.
Yeah, sure. No, I mean, it's also possible that they would just, within the first few seconds of of us turning them on, they would solve P versus NP and the Riemann hypothesis, and all of that other stuff, and then they would go on to, I don't know, just, abstract art,
We're telling stories to each other.
Yeah, exactly. So something that we can't even imagine right now.